Hello, this is AMAT362, Probability for Statistics at UAlbany. This is lecture 12. I want to remind you that in lecture 9, we considered the following setup. We considered the three M's, which is mean, median, and mode. Remember, these correspond to classical concepts such as the average for the mean, median, an example of which is the 50th percentile, and the mode, which is the most probable value. So you can sort of think of this as mu or x bar or E of x. Median, on the other hand, there's no real special symbol. Sometimes people use x or med, MED, or M. But you also want to think of this as the 50th percentile. And then for the mode, we have the most probable value. Which maybe mathematically you might write out as this is the value x that maximizes your probability mass function. So you try to maximize over all possible values for x, and you look at the probability for each of those, and then the largest one, the x that maximizes that is your mode. All right. So today we're going to revisit this topic, and I'm going to show you how all three of these concepts are actually subsumed by the mean. And this is going to eventually motivate the introduction to the standard deviation or variance of a distribution. So I'm going to think this is the intro to var variance and standard deviation. And we'll also see good reason to consider two other related concepts, which is namely that the expectation of the product can only be the product of the expectations in the case where x and y are independent. And so we'll be considering this situation. This is only for independent. And then the consequence of this is going to be that the variance of the sum only for independent, so that ends up also equaling the sum of the variances. Again, only under the assumption that x and y are independent. All right, but before we get that, I want to consider the broader question of how do these mean, median, and modes come about? I express them each as summary statistics, but they actually come about from trying to minimize some sort of error function, where we change the error function in each case to get these three different values. So the motivation is going to be is prediction. And again, prediction is such an important part of science and our society at large. Often you're trying to make an optimal decision, which involves you predicting something that you don't know whether it's going to happen or not. And then you're trying to maybe minimize some sort of error if you're wrong. So let's go ahead and formalize that. And in order to do so, we're going to need to recall one of these important formulas, which is that if x is a random variable, then when we study a normal function on numbers like g of x, we can compute the expectation of g of x. So then for g, a function, this is equal to the sum of each of these little g of x's, possible values x, times the probability of x equaling little x. So this is how you compute the expectation of a function of a random variable. We're going to consider 3 important cases where the goal here is we essentially want to do some betting. And so here's a situation where you might want to do this. So imagine we're in a situation where, so we're going to, so imagine we want to go ahead and do this expectation and prediction. So again, the picture that we usually like to cultivate here is that we have some space of possibilities, omega. We measure some number associated to each of these possibilities, such as, if we're counting the number of heads in a coin toss, where we toss that coin n times. And this all lands us in some sort of, heap of numbers. And if you sort of bend these numbers, you might end up getting some sort of distribution of what these possible outcomes look like. Now imagine we're in the following game where you don't know exactly what's going to happen, but you need to guess, and you'll be awarded money depending on how close you are to that guess. So let's imagine you're going to pick a value B, and then you're going to observe what the actual outcome is. So maybe you roll your die or what have you, and then you're going to win or lose money depending on how close you are to that value. All right, and so then you're going to let L of XB be the money lost if you predict B and the outcome is X. And so imagine I've kind of scaled this so that maybe the total prize is $1 million, but then you end up losing different amounts depending how far off you are from that answer. So the basic question here is, how should we optimize our strategy for picking B in order to lose the least amount of money or correspondingly gain the most amount of winnings? And again, you can sort of pass back and forth between these 2 different perspectives. I'm going to do loss just because that's the way it is in this beautiful book of ours, Jim Pittman, probability. This is following essentially the end of section 3.2 in this book. All right, so let's consider 3 situations, 3 different loss functions. And we're going to try to optimize our value for choosing B so that we minimize the amount of loss under each of these 3 situations. So in this first situation, we're going to imagine we have like an all or nothing. So explicitly what this means is, and again, we're looking here at LXB. That is our loss function. where it's going to be some amount, maybe 0 if X equals B, and then some amount of money, negative money, if X does not equal B. Of course, since we're saying lose, we don't need to incorporate that minus sign in there. So that's just the amount we have to pay, which might even be the cost of entry. All right, enough said. Let's consider what I mean when I say all or nothing. So in this case, I'm going to consider L of XB to be, we lose $0 if we win, and we have to pay $1 if we don't win. So again, if this is a game, you want to always take the sort of gambler's perspective, which is that you do this a bunch of times. What are your expected losses or winnings? So the idea here is we need to compute the expectation of L, which is a function of X. And again, we're then going to toggle our parameter B to figure out what's the best way to minimize our losses. So the big idea here is we're going to toggle B to minimize the expected value of L of XB. I'm going to use square brackets just to help separate out these two sets of parentheses. Doesn't really mean anything. Ordinary parentheses is fine. All right, so how do we do that here? Well, let's go ahead and enact it. So what's the expected value of my loss? Well, it's $0 under the situation that X equals B, so I have to weight that by the probability that X does equal B. And then I'm going to lose $1 under the event that X does not equal B. Now, of course, 0 is not going to affect our expectation, so this ends up turning into, well, whatever the probability of X not equaling B is, which is the same thing as 1 minus probability that X does equal B. So how do we minimize? Well, we can minimize by picking B to be the mode, which is also the most probable outcome. That's going to have the effect of maximizing this. And again, it's something that has to be less than or equal to 1. So if I maximize this, I end up minimizing this difference. So under this penalty function, choosing B to be the mode of X is the optimal strategy. All right, so let's consider a slightly different variation on this problem. So imagine you're penalized by just distance. So let me call this the absolute. So penalty equals distance. Again, the idea is you're going to predict a value B. X is going to produce some number. If that number ends up being close to your prediction, then you're only going to lose a little bit of money. Which again, if we're maybe viewing this as subtracting from absolute winnings, you're going to win a lot more money. But if the actual value is way off, then you're going to win less. All right, so what does that mean mathematically? Well, in this case, what we're going to say is that L of XB is going to be equal to the Euclidean distance on the real line. So that's X minus B. So the absolute value of X minus B. Now, how do we minimize this? Well, we're going to have to go back to essentially using calculus. So we're going to minimize the expected loss by taking the derivative with respect to b and set to 0. All right, but it's a little complicated because, again, the absolute value is not differentiable everywhere, but it is differentiable as long as you're not actually at that endpoint. So in particular, if I go ahead and try to compute what is the expectation L of X, well, I'm going to assume I'm in a discrete random variable, so there are only countably many outcomes. So I have that sum over xi, and then I'm going to take xi minus b, and then times the probability that big X equals little xi. So that's our definition of the expected loss. So if I were to try to differentiate this, so let's go ahead and do this ddb of E of L of xb. Well, I can use linearity of differentiation to say that this is the same thing as summing over each xi of ddb of the absolute value of xi minus b. And again, the probability in this case doesn't depend on b, it's, so you can just view it as a constant. Now, recall, if I've got my graph of the absolute value function, and let's say I'm in a situation where b is is over here, then you can see how the derivative of this is going to be negative whenever b is less than xi, and it's going to be positive if b is greater than xi. With just, again, the idea is that as you sort of increase b, the value is going to go down, so that indicates a negative distance. But on the other hand, if b were over here and I increase b, then my error could increase. So let's just go ahead and summarize that by saying something like, so I'll just say, recall that ddb of xi minus b is equal to minus 1 if b is less than xi, and plus 1 if b is greater than xi. And again, it doesn't have a value in the case where b equals xi, so we're going to assume that we're away from that. All right, well, so let's go ahead and now plug in these values for the derivative, and we're going to go ahead and separate out our sum so that maybe we're at some middle value. All right, so if I use this, so then the implication is that if I take the sum of the xi that are less than b, so again, b is greater than those xi's, then this contributes positively to this expectation. So I've got positive 1 times the probability that x equals xi. And then I can subtract when I've got xi greater than b, again, now I'm using the fact that I've already pulled out the minus sign, the probability that x equals xi. So this is a sum which we're trying to minimize. We're actually trying to set it to 0. And so with a little bit of thought, you can convince yourself that if, let's say b is between two values, xk and xk plus 1, or again, the idea here is, I'm labeling all my possible outcomes from lowest to highest value, x1, x2, x3, x4, x5, x6. And then I've got these little probability weights sitting on top of each of these. Then we're trying to find a value for B that sort of sits somewhere here. But anyhow, let's go ahead and just write this out formally. What does this look like? Well, this looks like the sum over x less than, let's say, xk. Because again, I'm assuming that B is between two values. So then times the probability that x equals, let me say xi. And then I'm subtracting times the probability of x equaling xi for xi strictly greater than xk. And I can actually lower this, go ahead and make that an inequality because I'm assuming B is between this. Now, if you think carefully about what this is, again, by the law of total probability, I'm just summing up the probability of disjoint events. So this is the same thing as the probability that x is less than or equal to xk, capital X, because I'm summing over all the outcomes that are less than or equal to xk. And similarly, this is the probability that x is strictly greater than xk. But if you rework this a little bit, this should be the same thing as -1 minus the probability that x is less than or equal to xk. So again, I'm just continuing this. This ends up equaling, well, if you combine those terms, you'll see 2 times the probability that x is less than xk minus 1. And this is the derivative ddb of my expected loss, which again, I want to set to 0 to minimize. But what does this say? Well, here you just need to find B between two values, xk and xk plus 1, so that the following equation happens. So choose B such that, well, again, set this to 0. I can see that this is the same thing as saying that xk is less than or equal to, or sorry, is equal to half. Or at least as close as possible to that. And so that is going to basically be our minimum, which we know is actually the median, right? So choose B to be the median. I'll have half of my probability on one side and half of my probability on the other. Let's do this one last calculation where instead of looking at distance, I'm going to look at squared distance. So here my loss equals squared distance. And again, just for sort of context here, if you think about your loss function, if I'm using absolute value, I have something like this. But if I'm doing squared, maybe for close values it'll be smaller, but then for large values it'll be bigger. So that's our x squared versus absolute value of x. So again, you might imagine there are different situations where using these penalties makes sense. So how do I? So just to say it shortly, so xb I'm going to say is x minus b squared. So this is, again, a function, so I can compute the expectation of L. And I can go ahead and actually use linearity of expectation in the following sense. This is the same thing as the expectation of x minus b squared. which is the same thing as the expectation of x squared minus 2bx plus b squared, which if I continue over here is the expectation of x squared minus 2 times b, the expectation of x, plus the expectation of b squared, but that just ends up being little b squared. So now let's do the same thing. Let's take the derivative with respect to b. So I'm gonna consider ddb of this. Well, expectation of x squared doesn't depend on b, so that goes away. Then I have minus 2 expectation of x, because b differentiates to 1. And then this turns into 2b, and I want to set this equal to 0. So to minimize. And then I'm led to the conclusion that the value of b, which I should guess that'll minimize my squared error, is the expectation of x. This is also known as the mean. So here, guessing the mean, b equals mu, which is the expectation of x, is best. All depending on these three different, or at least in this case, the choice of a squared error. And notice, just want you to step back here and think. All I did is I defined these different functions of a random variable, L. And I still use the same concept. I want to minimize my expected loss. That's E of L. But depending on the value of L, I end up getting at the three different summary statistics we introduced in lecture 9. I had the mode when the expected loss was just all or nothing, and either got it right or not. I got the median where my loss function was, well, we'll just use the distance from the right answer, and that'll be the amount you're fined. And then in the third case was, we'll square that. And then in that third case, the optimal choice was to actually guess the mean or the expectation of x. So that is sort of a characterization of how this concept of mean or expectation actually covers all the three concepts already introduced. Of course, it includes the ordinary mean, but it also includes the median and mode when you view these as functions of a random variable x. It means you have a sort of overarching theory that unifies all of them, and that is essentially considering expectations of functions. Now, we just figured out, so the sort of upshot is that for squared error, predicting b to equal the expectation of x is best. But that just tells you what's best. It still doesn't tell you what you can expect your losses to be, even when you choose the best possible value. So here's a natural question. What is our expected losses, which is going to be x minus our mean squared? Well, it turns out that this is exactly the notion of variance. And the closely related concept where we take this value and then take the square root of it is the standard deviation. well, let me correct that arrow. Turns out that this is the variance. So let me just go ahead and write that down as a definition. So here's our definition. X is a random variable, then the variance of X, which we write as var of X, is equal to the expected squared error, where error is measured as deviation from the mean. So this is the expected squared deviation from the mean. Now, if we don't want squared deviation, we just want ordinary deviation, we have to take the square root. And this is, for some reason, called the standard deviation. This is written SD of X is equal to the square root of the variance of X. And so I'm just going to go ahead and put these guys in colorful boxes because they're very important. There are other bits of notation which you might want to be aware of. So you can also write sigma of X is equal to the standard deviation of X. And correspondingly, sigma of X squared is also equal to the variance of X. And maybe I'll be lazy about capitalizing, A and R like I did here. But that's alternative notation. All right, but the rough intuition you want to have here is that in our sort of betting process that we're trying to do, in this prediction process, we're going to do a better job in cases where there are low variance. So that's low losses. And that corresponds to situations sort of like this, where maybe if I do my little histogram of values and this is my mean. And so again, you kind of imagine that I've done a little histogram here. But eventually we'll actually get at settings where there is a genuine continuous curve, and that corresponds to the setting where X is continuously varying. But for now, when we have situations like this, we're gonna have low variance. And this is to be contrasted with situations like this, where there's a much higher variance. And let's just go ahead and say that the mean is somewhere around here. Because again, that's our sort of center of mass, mu. So this is going to be this is a high variance. And this is a low variance. Where again, if I just look at the underlying curve, maybe that's what it looks like. And here I've got this. All right, so that's a rough concept. Let's go ahead and do some examples just so that we feel like we understand what this is. But I want to also note there's a special form for computing the variance. So here's another formula. So this is, I'll call this the alternative and this says that the variance of X can be computed as the expectation of X squared minus the expectation of X squared. Again, when I say it out loud, it sounds like I'm saying the same thing, but if you look at what I've written down here, there's a difference. There's the expectation of the function of X, which takes X and then squares it. So that's, here I'm taking the expectation of a function. Here I'm taking the expectation of X, which is just, the normal X times the probability of X summed over all values X. That gives me a number. And then I take that number and I square it. And the fact that these two aren't different, or are different, gives us a situation where we know that actually the variance is interesting. For a sort of quick proof, you can kind of imagine, well, if I just take what I just told you, which is that expectation of x minus mu squared, I go ahead and expand it, I get x squared minus 2 mu x plus mu squared. I use linearity of expectation, I get expectation of x squared minus 2 mu expectation of x plus mu squared. But then I recognize that this is also just mu squared, or sorry, it's just mu. Expectation of x is mu. And so then I have that this is expectation of x squared. One of the minus signs cancel with the positive, but leaving 1 minus mu squared behind. And so that completes the proof of that formula. Let's go ahead and see this in action, though, in some random variables that we've already considered. And remember, last lecture, we just introduced this concept of an indicator random variable. All right, so let's go ahead and do that here. So remember, we have this indicator. And sometimes people call this also Bernoulli. But the bottom idea is this is something which takes on one of two values, 1 or 0, and takes on value 1 with probability p. This would be the situation where your indicated random variable indicates whether or not an event occurs and where that event has probability p. And then it's 0 with probability q, which is 1 minus p. So again, we know that the expectation of x is just going to be, well, 0 times the probability that it equals 0, which is q, plus 1 times the probability that it's 1, which is p. So it's just p. Now, if we wanted to do this using the alternative formula, I could just compute, well, what's the expected value of x squared? Now, again, remember, all this is doing is I'm taking 0 squared, multiplying by its probability, and then I'm taking the value 1 squared times its probability. But 1 squared is just 1, so this still ends up equaling p. So now if I use my formula, I get that, that the variance of x is the expectation of x squared minus the expectation of x squared. This ends up equaling p minus p squared, which is equal to p times 1 minus p, or sometimes you'll see it written as p times q. So the variance of a Bernoulli random variable or an indicated random variable that's associated to some event with probability p, its variance is p times q. Now, one of the best ways of thinking about this in a slightly more concrete example is imagine I'm flipping a biased coin. So all this means is that, probability of heads is some value p, and the probability of tails is equal to q. You might ask, what value of p maximizes variance? Well, if you use this expression here for the variance, you get a pretty interesting answer. Now notice this is just a parabola that passes through two values, 0 and 1. There's 1, this is 0. And so you think of this variance as a function of p. So this is a variance of x. So if I had a process which maximized variance, it would be one where p equals a half. That's going to be our max variance. which ends up equaling, well, a half times a half is a fourth. So this also illustrates why a fair coin is one of the most canonical models in probability theory. It's literally the thing which has the most varied outcomes. Whereas like if I had a biased coin, one that came up heads only 10% of the time and tails 90% of the time, the outcomes aren't that varied. They tend to concentrate around probability of heads being 10. So then you'll see that actually most outcomes are tails. So if you count tails, you see it's been around 0.9. It'll actually be fairly tight in that sense too. So that's a situation where if you guessed, you would actually lose less money. So if you had to like guess the outcome, betting against a biased coin, if you knew what the bias was, would be preferable. It's not always true. It's not always possible, I should say. So let's consider another situation. And remember, you can think of this binomial, which is the sum of, and I'll use the phrase IID. So this is independent, identical, or identically distributed indicator random variables. So let's remember the way this works is that I've got my x, which is some x1 plus x2 all the way up through xn, where xj is 1 if the jth try is a success and 0 otherwise. And the idea here is that each try is independent of the previous one. That's what this independent and identically distributed means. Well, that's what independent means, is each try is independent. To say it's identically distributed is that the probability of succeeding each time is the same. It's P. So that we're going to write this down with the probability P, and here this is probability equaling Q, which is 1 minus P. So we already figured out how to compute the expectation of X. It ends up equaling N times P. But what if we had to compute the expectation of X squared? You might originally think, oh no, this does not look well, because if I did it the long way, I would say, well, let me sum over K equals 0 to N. That's the total possibilities of number of successes. And then I would take the number of successes squared, and then I'd take it times the probability that, X equals K. But this is complicated, right? This involves N choose K, P to the K, Q to the N minus K. So that's not a sum I want to actually compute. So luckily, it turns out that there's a general principle that we can use here. That means we don't have to compute it this way. So let me go ahead and just introduce that general principle over here. So here are two important facts. So they end up being closely related. So the first one is, if X and Y are independent random variables. So remember, this means that the probability that big X equals little x, big Y equals little y, or do this joint PMF that we've been doing, this ends up equaling the product of each of these two. And you can think of this as just being saying something like, oh, well, this is the same thing as probability of A and B, where A is the event that x equals little x, and B is the event that y equals little y, is equal to probability of A times probability of B. And again, this is an assumption, and it requires that it's not something that's true all the time. It's something that we need to check or be told that it's true. So if x and y are independent random variables, so if then the expectation of x times y ends up equaling the expectation of x times the expectation of y. And there's actually a pretty easy, quick way to check that this is true. So this ends up equaling the sum of little x times little y over all little x and little y of probability that x equals little x, probability that y equals little y, which by independence, we know that this is the x times y, probability that x equals little x, probability y equals little y. But if you sort of think carefully about it, you can just cluster these terms, turn it into sum of little x, probability of x equaling little x, y times probability of y equaling little y. And then you can just separate these out as two separate sums. And then probability of y, probability of y equal little y. And this is exactly expectation of x. And this is exactly expectation of y. The second principle, and I encourage you to try to prove it using the first, is that, again, if x and y are independent random variables, then the variance of x plus y is equal to the variance of x plus the variance of y. Now let's go ahead and apply that to the situation of binomials. So let's apply that. If I want to do x is the sum of IID Bernoullis, this equals a binomial, then I can compute that the variance of x, and hence the variance of a binomially distributed random variable out of n tries, probability p in each try, is equal to n times p times q, because this just equals the variance of x1 all the way up through the variance of xn, which is pq, all the way up through pq. So that's npq. So going back to kind of complete the chart here a little bit, over here, so by next page, we end up skipping this completely and just saying that the variance of x equals npq. And so you can actually use this to figure out, well, what's the expectation of x squared, which was this thing we were trying to kind of get at here. I'll remark that this is the example. This is also sometimes called the second moment of the binomial distribution. So just as a quick remark, e to the xk is called the kth moment of x. And so in particular, when you look at x squared, it's the second moment of your distribution. And this notion of moment actually comes from classical mechanics, where you think about like an object that you're swinging around. You also have things like torque and so on and so forth. And this is calculated in part by how mass is distributed through a body. Exactly the same analogy holds with probability. All right, well, that's it for today. I look forward to seeing you all in class soon.